Dear ladies and gentlemen, thank you for tuning in. My name is Sebastian Kühnert. I'm a risk analyst in the gas industry, and I did my PhD on functional arch and gauge models. Today, I would like to illustrate the core results of my work, lagged covariance and cross-covariance operators of processes and Cartesian products of abstract Hilbert spaces. I would like to begin with the motivation. Let X and Y be stationary UN, respectively Vn valued processes, where U and V are separable Hilbert spaces and Mn stand for Cartesian powers. I would like to describe the description within one process, X, for example, which can be done by lag-H covariance operators. These are cross-covariance operators of centered X null and centered XH, which can be identified as Hilbert space valued pendants of the autocorrelation function. I would like to describe the dependence between X and Y, which can be done by lag-H cross-covariance operators. These are cross-covariance operators of centered X null and centered YH and can be interpreted as Hilbert space valued pendants of the cross-covariance function. And my main aim is to estimate these operators while allowing the lag and also the Cartesian powers to vary with respect to the sample sizes. An example where it could be useful to measure the dependence between these abstract objects. For example, if we take a look at the monthly sunshine duration in June 2020 and July 2020, these realizations can be interpreted as realizations of an L2012 valued process. And we could ask ourselves, what effect does the monthly sunshine duration in Central Europe have on a portfolio 1 month later, for example, of power stocks? And these realizations can be interpreted as realizations of an L201 to the power 4 process, because every function is an element of L201, for example. Another example, we could ask ourselves, here we have a school of bluefin trevally chasing a school of bluefin anchovies. And the question is, has the position of the fish within each school have an effect on the position of each school? It certainly has, but we would like to measure the dependence. And we could also be interested in measuring the dependence between the whole school of bluefin trevally on the school of anchovies. I would like to describe the model now. Let's assume that we have weak dependent processes, X and Y, weak dependent in sense of L for M approximability. Then we define a big process as a vector of M values of this process, and for Y the same with Y's, but here's the vector length N, where we also have P here, which I will describe now, and Q. These can be understood as reusing factors. By putting P smaller than M and Q smaller than N, we reuse values of X for another element here, which is useful if we want to have a bigger sample size for the bigger processes. We can also just stack the elements in a vector, which is done if we put P equal M and Q equal N. And if values of X and Y here are missing, we can bridge them for these processes by choosing P greater than M and Q greater than N. Now I go to the estimation. Let's consider that we have a sample X1 to Xm and Y1 to Yn of X and Y. Of course, by the definition of the models before, the sample sizes for the big X and big Y's get slightly different. That's the reason why here are some variables which look different. And if we want to estimate the Lagrange covariance operators now of the big process X, we can use for centered X the moment estimator with slightly different limits than usual, which is because that we have to ensure that these values are well defined. If the first moment is unknown, we use a modification of that estimator where we also estimate the first moment. We do the same for estimating the Lagrange cross-covariance operators. For centered X and Y, we use the moment estimator with slightly complicated looking limits, but the reason for this is the same. We have to ensure that these values are well defined. And if the processes are not centered, and if we don't know the first moments, we use a modification of this estimator where we also estimate the first moments. So in order to derive asymptotic upper bounds where we also allow the lag and the Cartesian powers to increase, we have to assume that the Cartesian powers for the process X and the reusing factors are bounded or can increase with respect to n, but they have to be small o of n. Similarly, for the Cartesian powers and the reusing factors for the process Y, they have to be bounded or can increase with respect to n, but they have to be small o of n. Also, we impose that the lags are bounded or increase with respect to n and with respect to n, but they have to be small o of p to the minus 1n and small o of q to the minus n times n. Now I come to the main results. Assuming that all the assumptions before hold, we get consistent estimators. For centered X, the estimation errors have the following asymptotic upper bound in sense of mean. They are n to the minus 1, which is not surprising. But this time, if the lag, the Cartesian powers, and p, if they increase, it has an effect on the asymptotic upper bounds. But we get consistency if they are chosen appropriately. And if the process X is not centered, we get the same asymptotic upper bounds, but this time in sense of convergence and probability. The same holds for the estimation errors for the Lagrange cross-covariance operators. For centered X, we get the factor here, which is the factor of the estimator here, the Cartesian power of Y, of X, and the lag. And if these processes are not necessarily centered, we get the same asymptotic upper bound, but in sense of convergence and probability. Finally, I would like to point out that I also did functional principal component analysis of our covariance operators and also an extensive simulation study. Here are the main references I use for my work, and I thank you for the attention.